Hello and welcome to presentation number 2, Aggregates for Concrete. Aggregates are 60 to 75% of a typical concrete mixture. Therefore, the importance of aggregates cannot be overemphasized. If you have bad aggregates, you're going to have bad concrete. In a typical concrete mixture, aggregates consist of two sizes: gravel and sand. Gravel is typically 1.5 inch down to 3/8 of an inch, while sand is typically 3/8 of an inch down to the number 200 sieve. We'll talk about gravel, sand, sieve sizes, and sources in this presentation. So now, let's begin with aggregate sources and types. All normal weight aggregates come from rocks, and rocks come in three basic types: igneous, metamorphic, and sedimentary. Let's take a look at each of these individually. Igneous rocks can be considered intrusive or extrusive. The difference is where was the rock formed. If the rock was formed below the Earth's surface, it's considered an intrusive igneous rock, and if it was formed above the Earth's surface, it is considered an extrusive igneous rock. Intrusive igneous rocks are formed when melted rock, also known as magma, begins to push its way towards the Earth's surface, but it ends up getting trapped below the Earth's surface and cools. Once it cools, it becomes an intrusive igneous rock. Extrusive igneous rocks are formed when that magma makes it to the Earth's surface and becomes lava. Once onto the Earth's surface, it cools and becomes an extrusive igneous rock. Now, some common intrusive igneous rock would consist of granite, gabbro, and diorite. And common extrusive igneous rocks would consist of basalt, andesite, and pumice. Next is sedimentary rock. Sedimentary rock is formed because for thousands, even millions of years, tiny pieces of our Earth are eroded away by water, wind, and ice. These tiny pieces of Earth are washed downstream, where they are deposited at the bottoms of rivers, lakes, and oceans. Then, through time, pressure, and heat, this material is formed into sedimentary rock. Some common forms of sedimentary rock include limestone, dolomite, shale, and gypsum. Last but not least is metamorphic rock. Metamorphic rocks are rocks that used to be igneous or sedimentary, but through years of time, pressure, and heat, they turned into something else. As an example, we're all familiar with the diamond that was once coal. But we also have quartzite, which was once sandstone. We have slate, which was once shale. And we also have marble, which was once limestone. In fact, if you look closely at this piece of marble, you can see the layered material one on top of the other. Here is a diagram of a typical concrete mixture. As you can see, 67% of this mixture is aggregate. Ready-mix producers will always choose their aggregate first and foremost based on availability. They'll try to find the hardest, least deleterious, least reactive material. As an example, in New England, a great deal of granite is used, while out in Indiana, it is mostly sedimentary rock. And in the Palisades of New Jersey, it will be all basalt. And now that we know a little bit about where aggregates come from, let's take a look at their physical properties. Some of the aggregate properties we're going to be reviewing here include grading, specific gravity, unit weight, and surface moisture and absorption. However, there are a number of issues that you can research on your own that are critical to a concrete mixture. They include particle shape and surface texture, aggregates' resistance to freezing and thawing, shrinkage of aggregates, as well as alkali-silica reactivity. The first and arguably the most important characteristic of any aggregate is its gradation, or what's called particle size distribution. In other words, if we order 3/4 inch aggregate, we know that not all of it is going to be 3/4 inch. Some of it will be 1/2 inch, some of it will be 3/8 of an inch, and some of it even finer than that. However, the gradation greatly affects the properties of our concrete. For instance, in the plastic state, it's going to affect the workability and pumpability, and thus the overall economy of our concrete, while in the hardened state, it affects the porosity, shrinkage, and durability of our concrete in use. So let's go ahead and do an example of a sieve analysis. Whenever we do a sieve analysis, we start with the coarser sieves and move down to the finer sieves. Here we're going to be doing a sand analysis, so we'll start with the 3/8 inch sieve, move to the 4, 8, 16, 30, 50, 100, and then the pan. The 3/8 inch sieve is easy to remember, it's 3/8 of an inch. All the numbers mean is 4 openings per square inch, 8 is 8 openings per square inch, and so on. So you can see that the sieves are stacked from the coarser to the finer. We then pour our sample into the top sieve, and then we agitate the sieves for the appropriate calibrated time. So let's go ahead and go through the data sheet for the sieve analysis. Most governing bodies require at least a 300-gram sample for concrete sand. So here our original sample weight is 315 grams. The first column, which is highlighted here, should be the sieve sizes which we've used for this sieve analysis. Again, 3/8 down to the pan. Now the next column is, after agitation, we want to weigh the material retained on each sieve. So here, this is the weight retained in grams on each sieve. There was no material on the 3/8, 3.2 grams on the number 4, 47.3 grams on the number 8, and so on. Now the next column is the individual percent retained on each sieve. Not the weight retained, but the percent retained. So here, obviously, we had no material on the 3/8 inch sieve, therefore the percent is obviously 0. But then we had 1% on the number 4 sieve and 15% on the number 8 sieve. And again, the way that we get these percentages is we simply take the individual weight retained on a sieve and divide it by the original sample weight and multiply this number by 100. Next, we have cumulative percent retained. Cumulative percent retained is when we take the individual percent retained on any sieve and add to it all of the previous individual percent retains. So if we take a look at the number 8 sieve, for instance, we see that we have 16% cumulative percent retained. That comes from the individual on the number 8 sieve of 15, plus the 1% from the number 4 sieve. And if we move to the number 16 sieve, we have 33% retained, which comes from the 17, which is on the 16 sieve, along with the 15 from the number 8 sieve, and the 1% from the number 4 sieve. This takes us to percent passing, which is how most specifications are set up. Percent passing is simply 100 minus the cumulative percent retained. So on the first sieve we had 0% retained. 100 minus 0 is obviously 100. On the 4 we had 1% retained. 100 minus 1 is 99, and so on. And now we get an opportunity to see if our sand sample actually meets the requirements of ASTM C33. As we can see on the 3/8 inch sieve, the minimum and maximum for ASTM C33 is 100%, meaning that all of our samples should have passed through this sieve. And in fact, it did. Now if we take a look at the next sieve, the number 4, we should be between 90 and 100% passing, and we are. On the 8 sieve, we should be between 80 and 100, and we are. Therefore, our sample does meet the grading requirements for ASTM C33. And here is a final look at all of the numbers generated for our sieve analysis on our concrete sand sample. Whenever we complete a fine aggregate sieve analysis, we should also calculate our finest modulus, or what is often referred to as simply FM. We get this by adding up the cumulative percent retained on all of the standard sieves which are coarser than the 100 and then dividing this number by 100. Here we would wind up with an FM of 3.01. Now, the higher the number, the coarser the material. So it is important to note that this is only an index. In other words, we could have the same FM for different graded material. However, getting the FM on the fine aggregate is critical for mixed proportioning when we blend our sand with the coarser aggregates. This photo shows us why grading is so important. Let's assume that we have a bucket and we fill up that bucket with all 3/4 inch aggregate. It is not blended with any smaller material or any larger material. And now we fill that bucket up with water. For argument's sake, let's say that the bucket takes exactly 1 gallon of water. Now we empty the bucket and we fill up the bucket with 3/8 inch aggregate. Again, all 3/8, nothing coarser, nothing finer. And we fill the bucket with water. Well, that bucket would take exactly 1 gallon of water. However, if I mix the 3/8 inch material with the 3/4 inch material, I will reduce the amount of water necessary to fill the bucket, or in this case, to achieve the same workability in my concrete. And less water means stronger, more durable concrete. And speaking of water, let's now move on to moisture content and absorption of aggregates, as moisture content and absorption properties play a key role in the amount of water that will go into our concrete mixture. Our aggregates can be in one of 4 moisture conditions. They can be oven dry, which means that the pores inside the aggregate will absorb water. They can be air dry, which means that the aggregate surface is dry and some of the pores contain some water, meaning that they will continue to absorb water, but certainly not as much as the oven dry condition. Then we have saturated surface dry, meaning that the pores are completely filled with water, but the surface is dry. This is, in fact, the perfect condition. And then lastly, there is the wet condition. This means that we have moisture in the aggregate as well as on the aggregate. This photo shows you the 4 different conditions that our aggregate can be in. This slide shows us the calculations for both moisture and absorption. To calculate moisture, we want to take our wet sample and dry it out. Then we take the wet weight, we subtract from it the dry weight, divide it by the dry weight, and multiply this number by 100. For absorption, we would get the sample to the SSD condition, or the saturated surface dry condition, and then dry it out. Again, we take the SSD sample weight minus the dry sample weight, divided by the dry sample weight, and multiply by 100. Let's go through a couple of examples and explain why these numbers are so critical. Let's assume that we have a wet sample weight of 503 grams. We dry that sample out for 24 hours, and then we have a dry sample weight of 481. Here we would take the wet sample weight of 503 grams minus the dry sample weight of 481 grams gives us 22 grams. Divided by the dry sample weight of 481 grams gives us a number of 0.046 times 100. We have a total moisture content of 4.6%. Now let's take a look at absorption. Let's assume that we have a sample in the saturated surface dry condition of 499 grams. We're going to dry this sample for 24 hours, and after drying, the sample weighs 494 grams. Essentially, the calculation is the same. We take the SSD sample weight of 499 minus the dry sample weight of 494, and this leaves us 5 grams. 5 divided by the dry sample weight of 494 equals 0.01 times 100 gives us an absorption rate of 1% for this material. So how would these numbers apply to the real world? Let's assume that we have 1,200 pounds of sand and 300 pounds of water that's going into a concrete mixture. Our sand has 4.6% total moisture and 1% absorption. What adjustments would we make to both the sand and the water for our concrete mixture? If you'd like, please pause the video before moving to the next slide for the solution. So here's the solution. Again, we have to make two adjustments, one to the sand and one to the water. The first adjustment that we make is to the sand. If we need 1,200 pounds of sand and it has 4.6% moisture, if we throw 1,200 pounds of sand onto the scale, we haven't thrown 1,200 pounds of sand onto the scale. We've thrown a certain amount of sand and a certain amount of water. Therefore, we have to adjust for that water. We do that by taking the 1,200 pounds of sand, timesing it by the moisture content, and it lets us know that there's 55.2 pounds of water in that sand. And therefore, we have to weigh up 1,255 pounds of sand. Now we're also going to have to adjust our water because our sand has a lot of water on it. So here we need 300 pounds of water, and we're actually going to weigh up 1,255 pounds of sand, and we want to figure out how much moisture is on the sand. Well, that is 3.6% because the other 1% is actually absorbed. So we take the 1,255 pounds of sand times 0.036, the moisture that is on the sand, and that gives us 45.2 pounds of water on the sand. So therefore that has to be deducted from our 300 pounds of water that we want in the mix. So therefore we're going to weigh up 254.8 pounds of water. Now these calculations are also going to be performed for the stone. So let's go ahead and try this one before moving on to the solution on the next slide. Well, these are the numbers that we should have gotten. 1,800 pounds of stone, 1,155 pounds of sand, and the water that's going to be added to this mix comes out to 271.8 pounds. So how did we get those numbers? Go ahead and take a moment and look at the solution before we move on to specific gravity of aggregates. The specific gravity or relative density of a concrete aggregate is a critical value when proportioning concrete mixtures. We need these values to convert weights to volumes and volumes to weights. There are three specific conditions of specific gravity when referring to concrete aggregates. However, the most commonly used is bulk specific gravity, SSD, or the specific gravity of our material in the saturated surface dry condition. So now that we've had an opportunity to review the various stages of specific gravity, let's go ahead and take a look at how to calculate bulk specific gravity, SSD, of coarse aggregate. This is actually one of the easier calculations and one of the easier tests to perform. What we want to do here is weigh our coarse aggregate in the SSD condition and then weigh it underwater. We do this by simply taking the sample, putting it into a number 6 wire mesh basket, and submerging the basket with the aggregate in it. Once we have these two weights, we simply do the calculation B divided by B minus C, where B is the weight of the saturated surface dry sample, and C is the weight of the sample submerged in water. As an example, let's assume that we have a saturated surface dry sample that weighs 500 grams. We now put it into our wire mesh basket and submerge it. The weight underwater is 300 grams. We'd simply take the 500 divided by 500 minus 300 gives us a specific gravity in the saturated surface dry condition of 2.50. Lastly, let's review calculating the unit weight of aggregates, which falls under ASTM C29. This procedure assists us in determining the weight of coarse aggregate that will go into a concrete mixture based on a coarse aggregate factor. Let's review the steps of this procedure. One of the first things that we want to do in this procedure is calibrate our bucket. Here, what we're going to do is weigh the bucket empty. Let's assume that the bucket weighs 10 pounds. We're now going to fill the bucket with water. Once it's filled with water, we're going to weigh it again. Here, let's assume that the bucket and the water together weigh 41.2 pounds. We're now going to take the temperature of the water in the bucket. We can now deduct the weight of the bucket from the weight of the bucket with the water. This leaves us with just the weight of the water. We can now take just the weight of the water and divide it by a known weight. In this case, the weight of water for 1 cubic foot is 62.4 pounds at 73.4 degrees Fahrenheit. And if we take the 31.2 pounds and divide it by the 62.4 pounds per cubic foot, we'll wind up with a 1/2 cubic foot bucket. Now that we know the volume of our bucket, we can go ahead and weigh our aggregate. Here we need to select a procedure. We can use the rodding procedure, the jigging procedure, or the shoveling procedure. Once our bucket is full, we want to weigh it. In this case, let's assume that it weighs 55 pounds. We can now deduct the weight of the bucket, leaving us with 45 pounds of aggregate. Now we simply divide the weight of the aggregate by the volume of the bucket, and this will give us 90 pounds per cubic foot. As stated at the beginning of this presentation, the importance of concrete aggregates cannot be overemphasized, and this presentation is designed to simply give you a glimpse of their importance, but does not begin to scratch the surface of all that can be researched and reviewed in concrete aggregates. And this concludes presentation number 2, Aggregates for Concrete.